An N-channel MOSFET is conveniently drawn like this. The gate is here, the source is here, and the drain is here. The channel is between the drain and the source. The resistance between drain and source is controlled by the voltage drop between the gate and the source. In digital system design, we almost always connect the source for an N-channel MOSFET to ground, 0 volts. It is called source because it sources the electrons that move through the channel when the channel opens up due to an increasing gain to source voltage. Similarly, a P-channel MOSFET has got a gate, a source, and a drain. The source is almost always connected to the positive supply rail for P-channel MOSFETs in digital system design, and it's sourcing holes that then flow through the channel depending on the source to gate voltage drop. When designing digital systems, we normally consider FETs as operating at their two extremes. The first extreme is if the gate to source voltage is 0 volts, then the channel will have a very large resistance. So large, in fact, that we just assume that it's open circuited. It's as if it's a switch and the switch is off. No current will flow. The other extreme is when the gate to source voltage is sufficiently large that the channel opens up, allows electrons or holes to flow through it, and therefore it's got a very low resistance. So low, in fact, that we approximate it by a closed switch. 0 resistance, ideally. So the more refined model of a FET being a voltage-controlled resistor is replaced by the even cruder model of a FET being a voltage-controlled switch. By controlling the gate to source voltage, we can either have the switch on or the switch off. Remember, we can create an inverter using two FETs, a P-channel FET on top and an N-channel FET on the bottom. Using our crude model, we can understand how it works. If the input is a 0, then the N-channel FET at the bottom has got 0 voltage drop from its gate to source, and therefore its switch is off. The P-channel FET has got a 5 volt drop between its source to its gate and is therefore on. So in terms of switches, this switch is on and this switch is off. The on switch is connected to the 5 volt side, the off switch is connected to the ground side on the other side, so therefore clearly in this case the output will be 5 volts or a logic 1. Similarly, if the input is 5 volts, then we will have 5 volts from the gate to the source of this N-channel FET. This means that its switch is on. We will have 0 voltage drop across this P-channel FET, so as a switch it will be off, and the corresponding circuit is an off switch and an on switch, and so therefore the output is going to be 0 volts or a logic 0. Thinking of FETs as digital switches makes it relatively easy to design logic gates. We're going to design a NAND gate using just N-channel and P-channel FETs. Now, we always have the N-channel FETs on the bottom and the P-channel FETs on the top. You can experiment in LTSpice trying to do it some other way, but the consideration is the gate to substrate voltage, and you just can't get things to work if you try doing it the other way round. We don't need to worry about that in this course. Just remember, N-channel on the bottom, P-channel on the top. This means we'll always have an inverting design, and with some experience you'll know exactly what that means. But essentially, if we want to design an AND gate, we can't actually do it directly. What we'd have to do to implement an AND gate is to first implement a NAND gate and follow it by an inverter. And that's how you actually make an AND gate out of FETs. You can't directly make an AND gate with FETs. You indirectly make one, so to speak, with first a NAND gate and then an inverter. Maybe the very first place to start is with a truth table. So what we want to produce is a logic gate whose output is always a 1, except if both inputs are a 1, in which case we get a 0. In a FET design of a logic gate, we're always going to have a bottom half and a top half, and they're going to be duals of each other. When the bottom half is closed, the top half must give us an open switch, and vice versa. We therefore choose whether to start designing the bottom half of the circuit or the top half of the circuit. I prefer working with n-channel FETs, so I will start my design with the bottom half of my NAND gate. Keep in mind that we were after a circuit where we've got some n-channel FETs down here forming a digital switch, p-channel FETs up here forming a digital switch. The inputs will go into the gates of our FETs to determine whether the overall switch here is open or closed, and our output is taken at this halfway junction here. We've got ground down here and our supply rail up here. When we want the output to be a 0, we have to have this switch closed and this switch open. And conversely, when we want the output to be a 1, we have to have this switch closed and this switch open. This therefore determines what each of these two switches must be doing. We go to our truth table and we see that we want an output of 0 only when both inputs are a 1. So if this is a 1 and this is a 1, then this switch here must be closed. Otherwise, it's open. So the bottom switch is closed if and only if 1, 1 is at the input. I remind myself of how n-channel FETs work. I know that the bottom half can only use n-channel FETs, and with an n-channel FET connected to ground, if the input is 1, then this digital switch is going to be closed. And if the input is a 0, then this digital switch is going to be open. Remember, we said it was not possible to design an AND gate directly. We'd have to have a NAND gate followed by an inverter. Well, that's why things work out. Because this NAND gate is a so-called inverting gate, we require this switch here to be closed if both inputs are 1, and an n-channel FET does have the switch closed if the input is a 1, so therefore it is possible to make this design. If we were trying to do an AND gate from scratch, we'd get into trouble here not being able to complete this, and that's why to do an AND gate we have a NAND gate followed by an inverter. So the situation we're in is that we want this combined gate to be closed if both inputs are 1. I have a digital switch which I can close if an input is 1. So essentially I have got two switches and I want to arrange them in such a way that the overall switch is closed if and only if both of my individual switches are closed. There are really only two things I can do with digital switches. Either I can put them in series or I can put them in parallel, which is a bit harder to draw. There we go. Let's look at how they behave. If they are in series, then the overall switch is closed if and only if both of the individual switches are closed. And in fact, that's exactly what we want. If they are in parallel, then the switch is closed, the overall switch is closed, if a single one of these switches is closed. Indeed, the only way for this switch to be open is if both of the individual switches are open. For our NAND gate, we have deduced that this is the configuration we need for our n-channel FETs in the bottom half of our design. I will go through it again, but it turns out that we want this dual configuration for our p-channel FETs for the top half of our design, and putting them together we will have our NAND gate. For practice though, we will start again and design the top half of our circuit. If this top switch is closed, then the output's going to be a 1, and conversely, if this top switch is open, then we're going to assume that the bottom switch is closed, and that will make the output 0. Looking at our truth table, we see that we want the output to be a 1 if we have any input except for 2 1s. Rather than consider 3 different cases, it might be easier to consider the one remaining case. We want our top switch to function in such a way that if the inputs are both 1, then our switch is open, otherwise the switch is closed. Let's remind ourselves about how p-channel FETs work. If the input is a 1, meaning at the full supply rail, then the voltage drop between the source to the gate is 0, and so this FET is going to be closed or in the off position. If on the other hand the input is a logic 0, we have our full supply rail between the source and the gate, and so therefore the channel will be open and the switch will be closed. By the way, be careful with the confusing terminology. Switch being open and switch being closed mean the opposite of a channel being open and a channel being closed. Anyway, we're in the situation where we want this switch to be open if both inputs are a 1, and each individual switch is such that it will be open if a single input is 1. And remember, we can't achieve all possible combinations, but we know that we can make a NAND gate with p-channel FETs on the top, and so it will be possible to make this kind of a switch by combining p-channel FETs in either a series or a parallel fashion. What we want is for our combined switch to be open if and only if each of our 2 individual switches is open. If I had my switches in series, then my overall switch is going to be open if either of my 2 switches is open, which is not what I want. If on the other hand my switches are arranged in parallel, then I see that my overall switch is going to be open if and only if both of my switches are open. As soon as one of these switches is closed, the overall switch is closed. And so therefore I know that I want my p-channel FETs at the top to be arranged in a parallel way. In summary, we end up with our design here with our p-channel FETs in parallel and our n-channel FETs in series. Each input goes to a n-channel FET down below and a p-channel FET up the top, and our output is taken at the halfway mark. No matter what our inputs are, either the top half of the switch is going to be open or the bottom half of the switch is going to be open, but they're not both going to be open at the same time, and they're not going to be both closed at the same time. They're going to be opposite or complementary, or in mathematical terms, they're going to be the dual of each other. I have opened up LTSpice and I have a very simple circuit. Here is my FET and I have a variable input in here, V1. We notice this DC statement says that my V1 voltage is going to go from 0 volts to 3.3 volts in increments of 0.01 volt, and we can compute the output for each of these input voltages. In this way we understand the steady state behavior of this FET, and we will hopefully see that it does essentially behave like a voltage controlled resistor. My supply rail is given by V2 up here at 3.3 volts, and it goes through our resistance R here. So if you like, this is my pull-up resistor. If this FET's channel is completely off so that no current flows through it, then this pull-up resistor will mean that the output is at 3.3 volts. As I increase the gate voltage, because the source is at 0 volts, this increases the gate to source voltage drop. My channel should start to open up, currents should start to flow through here, and my output should come down from 3.3 volts all the way down to close to 0 volts, depending on how wide open the channel is. The resistor R here is also going to be varied. I have 4 different settings here. We are going to get 4 different graphs. One when R is 1K, another when it's 10K, another at 100K, and the last is when R is 1 megohm here. Of course, the size of this FET determines what its resistance is going to be at the extremes. And so, depending on how big or small this FET is, that changes what a suitable value for this resistance R is here. Notice that for this MOSFET, and this is typical in an older CMOS chip, I've actually specified the length and the width of the gate. That will be more meaningful in a subsequent part of this video series. Anyway, let's go simulate this now. So we go up to the little running man and press the run button. I then want to rearrange the windows to make things look a bit nicer. And I've got my circuit on the left. At the moment I've got no waveforms here, but all I do is as I move the mouse around my circuit, you see that I get a little probe icon showing up, and so I can look at the output by clicking on it here. We get these 4 curves because my resistor R takes on 4 different values. So each of these curves corresponds to a particular value of my resistor R. Furthermore, I have got my input voltage V1 varying. Because it's linear, in fact, we can read off the input voltage along this axis here and the output voltage along this axis here. If you prefer, I can click on the input V1, and so we see that truly the input just increases in a linear way. Going back to just my output traces, we can now try to make sense of this figure here. When the input V1 is very small in this region here, the gate to source voltage is very small. That is not enough to make this channel open. In fact, there's a threshold. We see that up until just past 0.6 volts for this particular FET, the channel does not start to open up. It's only once we've passed this threshold voltage here that our channel starts to open up. What that means is that the resistance between drain and source goes from being approximately infinite, of course it's not really infinite, but approximately infinite, then when the gate to source voltage crosses the threshold, it starts to decrease down to reasonable values. And that decrease is fairly sharp. There's a sharp transition here. At the other extreme, let's look at this other extreme next at 3.3 volts. That's when we'd expect for this particular FET its channel to be wide open as it's going to get. Now ideally there'd be 0 resistance, but FETs do have some inherent resistance even if they're wide open. And that's why we see at 3.3 volts when this FET is wide open, even though in some cases the output is essentially 0, it's not always 0. So we should be able to deduce which resistance value this green curve corresponds to. Remember, each of these 4 curves corresponds to R up here being 1K, 10K, 100K or 1 meg. Well, let's assume that the resistance between here and here is, and I'm just making this up, let's assume it's 10 ohms. It's actually probably going to be larger. In fact, we can work out how large it is. It's actually going to be approximately 1K. So let's assume from here to here is approximately 1K. Well, that means that if this is 1K and this is 1K, then the output here should be halfway between these 2 voltage levels. And that's why we see for our green curve here that we're actually at this level here. Now, maybe for this FET, the channel can have a lesser resistance if we increase the input voltage even further, but I'm choosing to drive this with 3.3 volts. It's just for us to get an understanding of how FETs work. If our resistor up here is larger, even if this is 1K, if this were say 1 megohm, then 1 megohm is so much bigger than 1 kiloohm that our output is going to be very close to 0. And remember, in practice we're going to have a p-channel FET sitting up here, and its channel impedance can be extremely high when it's turned off, and so therefore we're going to see traces more like this cyan coloured one, meaning that when this FET is on, this FET up here is going to be off, and so the output's going to be very close to 0. Let's now look at an actual inverter. Here's my n-channel FET again. here's my p-channel FET. Now if you look closely, you'll actually find, although they have the same length and width, this mobility parameter is different for the two of them. For the N channel, I have a mobility of 1, and for the P channel, I have a mobility of 4. And this comes from Cedar and Smith's book on microelectronic circuits. It explains that due to the differences between electrons and holes, you're going to get different performance out of two same-sized FETs, depending on whether they are N-channel or P-channel. It's not an issue for this course. I'm just trying to be a little bit more realistic. My V1 supply is just my positive supply rail, and it is operating at a VDD of 3.3 volts. V2 is the input to my inverter. Remember, an inverter is made out of an N-channel FET on the bottom and a P-channel FET on the top. So V2 is the input. It's a variable voltage, and I am going to vary it between 0 and the positive supply rail in increments of 0.01. Now for digital circuits, you may well say, but the input's either going to be 0 or 1, i.e. 0 or 3.3 volts. But firstly, the input can't magically jump from 0 to 3.3 volts. It has to transition through all the other voltages first to get there. And also, a 0 volts would imply that there's absolutely no noise, no corruption, our circuit's absolutely perfect, and that's not true in practice. So it's important to, at some stage in this course, ask the question, what happens if I put in an actual analog waveform into my inverter? What do I get out? And we can find out by running our simulation. Then I'm just going to rearrange the windows. Once again, I'm not going to click on it, but if I did, I'd see my input just rises linearly, and I can then see the response of my output by clicking on it. And we get this very typical curve here. The horizontal axis is my input voltage of my inverter at the two gates here, and the vertical axis is the output voltage right here. This is the steady state performance. If I were to put in a very high-speed sinusoid into this, I would get out quite an interesting response because these FETs have got capacitances, etc. But we will worry about that another day. In terms of the steady state response, we see that there's this very nice sharp transition here. And later we will learn that this really helps increase our robustness to noise. Essentially what it's saying is that it doesn't matter whether the input is exactly 3.3 volts. Even if the input is at 0.6 volts, the output is going to be a perfect 1. It's essentially indistinguishable from the full supply of 3.3 volts. So it means that I can have a noisy input, but the output's going to be very clean. And this is what makes digital circuits so effective at processing signals. If you were to get out your cursor, you will actually find that the output is not at the halfway point when the input is at the halfway point. Although this diagram looks very symmetric, remember I mentioned that P-channel FETs don't perform as well as N-channel FETs, so there's a little bit of asymmetry going on in here due to the mobility factors of holes and electrons being different. But regardless of this, and there's a factor of 4 difference by the way, so it's non-trivial, regardless of this, we see that it's actually very close to being near the center too, meaning that this design is quite robust to variations in the FET characteristics of the N-channel and the P-channel. The way we explain this diagram is exactly in terms of these FETs being voltage-controlled resistors. As the input voltage here begins to rise, this channel, once we've passed the threshold anyway, this channel is going to start to open up and allow electrons to flow, and this channel is start to close, restricting the flow of holes there. So we've got one resistor here, the other resistor here, the output is given by this voltage divider. And so we get this nice transitional curve here. The fact that we have such a steep transition, firstly, as I said before, is very important for noise robustness. suppressing noise effects. But it's also due to the fact that these channels can open up quite quickly. So we can go from a channel being very high impedance, well over say 10 megohms, to suddenly being quite a small resistance here opening up. And that rapid change in the resistance here, as we change the input voltage, causes this very steep drop here. Here is a sneak preview of a circuit we're going to be discussing later in this video series. The previous circuit we looked at was just a single inverter. Its output was not connected to anything, which is somewhat unrealistic, and its input was a steady state voltage. Although we varied the voltage, we did so in a very slow way, so to speak, so that we were always computing the steady state performance of our inverter. This time I'm going to put in a high-speed pulse into my simple inverter here. And I'm also going to load it with the input to another logic gate. In this case it's another inverter, but the point is, if the output of this inverter does not have to drive anything, then it's a lot easier for these FETs to supply the necessary current needed here. As soon as a logic gate has to drive one or more other logic gates, its performance changes. And by the way, we will learn later that this means you cannot take the output of one logic gate and let it drive 100 other gates. If you did that, you're just not going to get the performance you'd expect at all, because each gate loads it up, makes it harder for this FET to switch quickly. Let's have a look at what happens when we run this. Press the little running man icon, rearrange the windows, and I am just going to look at the output of the first inverter. These files are available online, so you can have a look at other voltages. I'm just going to have a look at the voltage here. Now remember, the input is a pulse. In fact, let's display it. So this blue curve here is the input going into my first inverter. And what we get coming out does not look like a nice pure digital waveform at all. We see that, let's have a look at this one here. When my input goes from a logic 1 to a logic 0 in a nice beautiful way, because it's generated digitally, via computer simulation I mean, when we have a nice change in my input, the output voltage suddenly zooms down to a negative value and then rises up slowly until finally becoming the correct value at the output here. And then at the next transition, the output shoots off up to 4 volts and then slowly drops down until becoming the correct 0 volts. So these are the transient effects. And in fact, digital systems are very noisy. When you design a system that contains some digital and some audio electronics, you tend to try to keep the two apart because the digital system is very noisy and can interfere with the analog system. The reason for this behavior is going to be discussed later, but this is part of the reason why it's important at some stage to actually look at how digital systems are made, because we can't always assume they're these nice circuits that produce zeros and ones. They're not. They're actually analog circuits, and there are points when we do need to treat them as such. Most of digital design is about working with zeros and ones and building circuits without worrying about this, and that's the power of digital design. But when we come to interfacing our circuits, when we come to actually building them on PCB boards, etc., we need to really consider about the analog side of things. We have now seen there are 3 ways of simulating digital systems, and it's worthwhile remembering what each one does. First, we have our functional simulation, and this does not involve any delays in the circuit. We are assuming all our logic gates and flip-flops are perfect and there are no delays whatsoever, other than the synchronization caused by having a clock in such designs. This is the fastest simulation possible, and therefore it's used to work out whether or not we've made any silly mistakes. It won't catch complicated timing mistakes, but it will catch basic mistakes. Keep in mind that in our workshops we've been designing relatively simple circuits, so compile times and simulation times are not very long. If you have a very large design, such as designing a whole CPU, then simulations can take a very long time to run. It's therefore important that we have some way of catching silly mistakes quickly. You don't want to make a silly typing mistake, wait 5 hours for the test results to come back, only then to go back and fix the silly typing mistake. Next, we have our gate level simulations. These ones incorporate timing information. At least Quartus does its best to do that. It includes the delays from signals passing through the input-output buffers into the FPGA. It includes wire delays for signals travelling between different logic elements and logic array blocks, and it also includes the intrinsic delays of your lookup tables and your flip-flops. For large designs, gate-level simulations normally take a lot longer than functional simulations, which is why you don't immediately run gate-level simulations. You first run your functional ones to check for no silly mistakes, then you run your gate-level ones. Now, in principle, if your gate-level simulations work, then the FPGA design should work, but with some caveats. First, except for very trivial circuits, it's not possible to test every single possible input with a gate-level simulation, and therefore your design might still contain mistakes, you just didn't test for those in your simulation. The second caveat is that this only checks what's happening inside the FPGA. Signals have to get to the FPGA pins, and if those signals don't meet the timing requirements or are somehow corrupted due to the PCB design, etc., not taking into account the high-speed nature of digital signals, etc., then again, your design might not work. So just because you pass gate level doesn't mean you will work for sure, but it is getting a step closer. Just before, we've seen that we can also simulate digital circuits using SPICE, an analog circuit simulator. In principle, it would be nice to simulate your whole design in SPICE. In some ways, it's the most accurate of these three simulators. The trouble is, it will just take way too long. For complicated designs, I don't believe it's even possible to have a full SPICE simulation over any significant period of time, especially not one able to test all the millions of possible inputs that a gate-level simulation can do. The simple description is that as we go from functional to gate-level to SPICE simulations, it takes longer to do the simulation, but we get a more accurate result. Now that's not to say we get a perfect result. Even the SPICE simulation is not perfect. People are still developing new models for FETs to work out how they work at high frequencies. So simulations are never perfect, but they do aim to give us more and more accuracy as we move along from functional to gate level to SPICE simulations. In practice, you will rarely see SPICE simulations of digital circuits. You might see them near the output ends to try to work out transient responses and the way different devices talk to each other, etc. That's under high-speed design, and they have some other tools to help them there too. The main reason I've shown you SPICE is because I believe it's very important to understand that while most of the time we work with zeros and ones, underpinning all of that are true voltage waveforms, and they are not ideal, and at some stage we do need to consider their imperfections. Perhaps even more relevant is that we have been discussing propagation delays and contamination delays, and even setup time and hold time, and it's through SPICE simulations that we can understand where these delays come from, and we will also be able to use SPICE simulations to see how a flip-flop can become metastable.